In this section, we're going to talk about safety issues and explore the potential hazards in a little more detail. And I showed this picture before just to show you all of the different safety approaches that were used more than half a century ago. Of course, today, most of our approach would not allow just simple administrative controls and training of the individuals and have them in a potentially hazardous UV environment. We'd like to see much stricter control measures today than people were accepting quite a few decades ago. One question that the occupational medical people generally ask is whether there are special issues of phototoxicity, because everyone's fairly experienced with the fact that there are some medications that photosensitize you, some very common antibiotics like tetracycline, and this becomes a problem primarily when somebody is working with near UV, ultraviolet A lamps, for non-destructive testing, for fluorescence testing, for insect control, and so on. This is because the pharmaceutical, or it could be a cosmetic, or it could be an endogenous chromophore, such as porphyrins in some people with some dermal disorders. That chemical adds to the energy of the photon so that you can get a biological effect that's more similar to UVB from a UVA photon. Now, those same chemicals will hardly add any energy to UVC photons. UVC photon has enough energy to cause all the biological effects. So normally you don't think of any sort of phototoxicity issue when you're talking about special photosensitivities. The accidental overexposures to germicidal UV are fortunately quite transient. There's perhaps one or two reports in the medical literature of enormous overexposures, like thousands of times above the permissible exposure limits, where no doubt because of the UVB that's considered trace amounts at the exposure limits can become the key biological agent when you have such enormous overexposures. So one really does have to pay attention to the safety. You don't want the complaints of someone who is a painter and moved up into the upper room to paint and didn't know that there was a germicidal UV lamp up there. And they normally complain just of photokeratitis because the thresholds for erythema are a good bit higher. The photobiological band UVC then has the benefit of very shallow penetration depths and therefore high safety compared to UVB. And the second benefit is that there's a strong bioaerosol absorption. Now, the newer lamps known as far UVC excimer lamps at 222 nanometers are much safer than the low pressure mercury 254 nanometer lamps. But there's still questions that have arisen about krypton chloride excimer lamps. The 2022-2023 ACGI-HTLVs have elevated exposure limits for those, but there's still people questioning how safe that is. And remember, we showed this figure before, that wavelength is very, very important. And the effect is seldom from just one wavelength, but we have this weighting factor formula shown on the left. The permissible exposure limit is 3 millijoules per square centimeter after everything's been weighted. So if you had a single emission like an LED at 270 nanometers, the peak of that solid curve, your permissible limit is 3 millijoules per square centimeter, which works out to be 0.1 microwatt per square centimeter over an 8-hour period, time-weighted average. If expressed in joules per square meter, as sometimes done when you're talking about outdoor sunlight exposure, it would be 30 joules per square meter. Now let's take an example of 254 nanometers, which is not at the peak 270. S lambda, or that solid line, it has a value of 0.5. So the equation up on the left, we would use the irradiance that we measure, but we'd multiply it by 0.5 so that the effective irradiance, E sub effective, is twice as high as for 270. So at 254 nanometers, this is 6 millijoules per square centimeter delivered in different emissions during the day, but it's the total cumulative 8-hour exposure. Or the time average irradiance is 0.2 microwatts per square centimeter, just twice that would be permitted if you had only 270 nanometers. So now if you go down to something like the lower end of that scale, well, let's try 222 nanometers. It's more than a tenfold down. You could have, instead of a tenth of a microwatt, you could have several microwatts per square centimeter over a day. So there's a very large safety margin for exposure of the skin. And there was an effort then in 2022 to split out action spectra. If you have eye protection, you could have higher exposures for the skin. So there's actually a TLV for skin where the eye is protected. And some of the reason there's a lot of interest in 222 nanometers is the fact that the absorption coefficient of most proteins and so forth really skyrockets below 240 nanometers. And so there's a bar there at 222 and another bar at around 207 nanometers for two different types of excimer lamps. And the reason that those wavelengths can be biologically effective in activating viruses is because that energy is absorbed more, and so there can be more of an effect. So what are the protective control measures? First of all, eye protection in case someone is not wearing protective clothing. Otherwise, you have to make sure that the lamps are installed properly, and we do not have the technicians in this country in sufficient numbers to have widespread use of germicidal lamps again, regardless of whether they're the short wavelength or the traditional 254. And we actually went through this before. I just am trying to review key points for you. That the most important takeaway is, although IARC has classified ultraviolet radiation as carcinogenic, the relative risk is enormously less for UVC. So years ago, the traditional fixtures in the 1950s were these open units which had a big reflector, and it was not louvered to irradiate the whole upper room. But in those days, most indoor rooms had pretty high ceilings, and you could get away with this without a lot of reflections off the ceiling. Today, the idea would be, if we had a safe UV wavelength, such as 222, we could actually have the energy directed downward. Now, in some operating rooms, they actually have this whole room irradiation set up, and between procedures, when nobody's in the room, they can have very high levels, and they have safety interlocks on doors and so forth. Some of us have argued that the eyes inherently have some shielding from overhead UV because we've evolved upper lids that always block radiant energy from the sky and the sun above 45 degrees, even lower angles when in bright sunlight. So the brow ridge and the upper lids block much of the overhead UVs. So we would be concerned about UV exposure reflected off of walls and so forth. And the HGH limits provide the guidance for measurement that you don't have to have a full 180 degree field of view of your instrument, you can get by with 80 degrees because that simulates the primary angles of risk of exposure to your eyes. So you would direct a cone radiometer that just looked at the central 80-degree field of view at the source and say, okay, this is how long you could stay in this particular position. So the top bullet there states that a higher horizontal irradiance falling on a horizontal surface could be permitted than with a vertical wall-facing lamp system. And just to explain that a little further, most people are not aware of the fact that their upper lids act as sunshades, awnings, if you will, that automatically lower as the brightness of the sky goes up and the intensity of the UV goes up. So 45 or 50 degrees is your upper limit at nighttime, or if you're indoors, 30 degrees is typically for a sort of overcast day, and 15 degrees is rather typical for people in really bright outdoor environments like out in the desert or at the beach. So overhead sky light, which has a lot of UV, actually is blocked by the upper lid so that you don't get snow blindness. And as the name snow blindness implies, even in the late winter and early spring, when the sun is not that high in the sky as in midsummer, the real cause of photokeratitis outdoors is from highly reflective ground surface, like snow reflects 85% compared to grass, which really green grass reflects less than 1%. So all of these factors have led to a better specification of our exposure limits and safety guidance for UV. So the newer UV fixtures actually produce a very collimated band of light, as shown here. There's some wall-mounted units on the left and the right, and then there's this 360-degree unit in the center of the room, and they irradiate a volume of air that's only about a foot in width, maybe 7 or 8 feet above the floor surface. These types of highly louvered modern germicidal fixtures with mercury vapor lamps are much less likely to be wrongly installed or moved. Some of the earlier ones, there were guys that would install them on the wall and say, gosh, this thing's aimed upward towards the ceiling. That's not going to do any good. We need to aim it down into the occupied space where it'll help, and not realizing how risky that was. So with all of these, there's extensive maintenance required, like cleaning the lamp every year, depending upon how much soot there is in the air indoors. Hopefully not much. They do have extensive experience in some large buildings, but germicidal UV in the workplace is fairly limited as of today. So some of the control measures for germicidal UV, often called UVGI in the past, would be to limit human access, limit duration of exposure. And so one can consider the occupancy factor and duration of access so that you can employ time-weighted averaging and have higher levels than would be if you have an occupied space for 8 or 10 hours a day. If you don't set up these types of safety procedures and you have an accidental injury, you'll have quite an angry victim. And UV lamps germicidal lamps were used widely in operating room theaters a half century ago or longer. And in almost every case, they were removed after someone on the surgical staff didn't properly fit their eye protectors because they had to have complete coverage with gowns and so forth. And they suffered an eye irritation or painful photokeratitis, and they went to the hospital administrator and insisted that things be removed. And I can remember talking to a few surgeons who had practically tears in their eyes. They were so angry because they thought that the benefit greatly outweighed the risk. So our benefit versus risk equation was being questioned there. Particularly in orthopedic surgery procedures, we actually still have some still employed, but the staff have to be properly trained to take precautions. A big issue from the engineering installation of germicidal lamps is knowing how much your ceiling is reflecting if you're using upper room germicidal units. And these are two plots of spectral reflectance. How much UVC is reflected is a function of wavelength for different types of paints and different types of ceiling tiles. And it's not important to know what all these different ceiling preparations are. But as you can see, there's one group which is really low, which would be ideal. They're reflecting less than 1%. And then there's another group that goes anywhere from 10% to 50% reflection. Now, if you had an installation where people were always protected, you might actually want high reflectance of ceilings and wall because it would enhance the amount of exposure of the air and improve the disinfection rate. Some of the types of paint surfaces that were problematic would be gypsum paints because gypsum is quite reflective in the UVC, but most paints are quite absorbing. Now, I mentioned that there are UV lamps that are placed in ductwork, and here are two examples. Their efficacy is not nearly as good as irradiating the entire upper room or the whole room, but at least for a couple air changes per hour, it is providing some disinfection. And there are different designs. The important safety issue with this type of installation is that they really have to have workable interlocks, and the people that are cleaning the hoods and changing the lamps, they have to be properly trained or somebody's going to get injured. During the early days of the pandemic, there were a lot of online sales of handheld UV germicidal wands, and these were discouraged strongly by the FDA, Center for Devices and Radiological Health, and by other safety organizations because they weren't very effective to start with. Germicidal UVC is far less effective at disinfecting surfaces than use of normal household cleaners, but they're indispensable if you want to disinfect air. So the whole concept of these little handheld devices was poor or misinformed. Nevertheless, there were millions sold, and even the dollar store were selling little inexpensive ones for $1.25. And so I bought several. They're very useful in terms of calibrating instruments and a few other things, but not as a germicidal application. There are different types of warning labels that have come up for germicidal, and these never have become very widely used. I'll stop here by finishing that we have a two-edged sword here. The germicidal efficacy requires that the photon have a lot of high energy and some penetration depth, but safety is most challenging when you have the higher photon energy and you don't have adequate protection, particularly of the eyes. So there's many factors that demonstrate efficacy, and we don't really have time to go into this, but if you're interested, there are books written on germicidal UV, and the most widespread use of germicidal UV is actually in water disinfection currently. And of course, in these cases, the energy is totally absorbed inside the pipe, and it's been a real success for ultraviolet lamp technology. It's quite a large market. And the last thing to point out is that there are big variabilities depending on the microbe and its structure. And we see that in these different relative action spectra that were performed using short wavelength lasers to better define action spectrum. I think that's pretty much it. I enjoyed the opportunity to talk about one of my favorite subjects.